thank you all for coming. I'm going to talk to you guys a little bit today about the research I was able to do this summer with my professor, Dr. Lou Ludwig. As the title suggests, I'm going to be talking to you guys about links, which is traditionally a subject that's broached in knot theory. But today I'm actually going to talk about its application in the realm of graph theory. So hopefully there'll be something here for everybody, you graph theorist or knot theorist or not mathematician. So without further ado, let's get on to what I'm going to talk about. First, I'm going to broach some previous works and previous articles that have been written on the area, and specifically some motivation for the particular question I'm going to be talking about. Then we're going to get on to some results that I was able to come up with over the summer, and finish up with some open questions that have yet to be answered, but hopefully will be answered in my senior year as my part of my senior honors thesis. So let's get going. In 2001, an article was written by Drs. Flappen, Naney, and Pommersheim. It was a pretty lengthy article, about 8 or 9 pages, but they were able to actually prove a pretty interesting result, namely that K10 was intrinsically triple linked. Now, I know what you're saying. That's a pretty great result, right? A few of you probably don't know what that means. So let's get through it. When I talk about K10, I'm really just talking about the complete graph on 10 vertices. Well, what do I mean by a complete graph? Well, a graph is just a collection of vertices and edges, and when I talk about a complete graph, I just mean that between any 2 vertices that we have an edge. So over here we would have an example of 5 vertices and the edges between all those vertices. So this is just K5. So when we're talking about K10, just imagine there are more vertices and everything. So I'm going to get to intrinsic linking in a little bit, but let's just talk about what a link is. Well, topologically speaking, a link is just when we're talking about 2 or more closed loops in space and how they relate to one another. So over here I've got an example of 2 closed loops, 2 triangles, and we have this link. Now, a link is just when you have them connected and you can't separate them without breaking an edge. Now, obviously, you can have any number of closed loops, and then in so doing, you can have any number of links. But I'm going to be talking to you about 3-component links, or triple links. And this can actually occur in one of 2 ways. We can have this sort of bridge loop right here connected to the other 2, where the other 2 do not link to each other. Or we can have sort of a pairwise linking scenario in which any 2 of the loops link to each other. So both of those will manifest themselves in our complete graphs, and we're going to be looking for them, but just know that they can happen in both forms. Now, what do I mean by an intrinsically linked graph? Well, technically speaking, intrinsically linked graphs means that in every embedding of that graph, we have a link. Well, what do I mean by that? Well, if I were to give each and every one of you 10 vertices, and I were to give you enough rope to connect all those vertices and complete the graph, no matter how you worked that graph, no matter how many bends you put in those edges, no matter how you move the vertices around, no matter how many times you tried to trick me, every single one of you would come up with a graph that had a triple link in it. Now think about that. That's pretty impressive. No matter how you worked that graph, as long as you completed it, you would have a triple link. So that's pretty impressive. They were able to prove that in about 8 pages. It's almost as impressive as the Conway and Gordon result from the 1980s, in which they were actually able to take 6 vertices, complete that graph to get K6, and they were able to prove that K6 was intrinsically linked. So not triple linked, but just 2-component linked. So they're actually able to step that up here in 2001. Now, if you think about it, 10 vertices is kind of a lot. If I was talking about closed loops and I was really just talking about triangles, and we want a triple link, well, it stands to reason that we really only need about 9 vertices, right? We need about 3 triangles to get our triple link. Well then, what about K9? Let's see if they had anything to say about K9. Well, in the same article, they were actually able to prove that K9 was not intrinsically triple linked. So anybody got a counterexample for that? Maybe it looked something like this. Yeah, that's a pretty interesting graph there. They actually were able to put this in at the end of their article. It's a clean graph, but and the beat of itself, it is not triple linked. So they were actually correct in that assessment. But if you look at it, some of these edges are doing some interesting things. They're actually like weaving in and out of each other. They're causing a few little interesting crossings over there. But this isn't triple linked as a K9. But you know, is that it? Do we just break down? Do I end my talk and go for coffee or something? Unfortunately, no. We're mathematicians here, or at least I am. We're going to push this result. We're going to say, you know what? Why don't we just start from K10 and see what we can get from it? And that's exactly what Dr. Bull and Foisey did. They took in 2004. They said, you know what? Let's take this K10 and start removing some stuff. Maybe we can get a better result and get something that's intrinsically triple linked. So what they did is they took our K10 and they said, you know what? Let's take 4 edges incident on 1 vertex. Take that out of the picture, and they were actually able to prove that that's still an intrinsically triple linked graph. So that's pretty interesting. They were also able to take 2 edges that were not common to 1 vertex, remove those from the graph, and it's still intrinsically triple linked. So that's pretty hopeful. They've been able to whittle it down a little bit. But notice that they've been actually working with linear embeddings of K10. What's a linear embedding? linear embedding is just a fancy way of saying straight edges. So if you noticed in the counterexample, the edges were kind of moving all over the place. They were bending and weaving in and out of each other. In a linear embedding, we're stuck with straight edges. These edges can't break one another, and though we can stretch them out and kind of move them around in space, we can't bend them at all. So it's kind of rigid. And why is that important? Why are linear embeddings important? Well, there actually happens to be a pretty interesting link between linear embeddings of graphs and molecular chemistry. So if you think of the atoms as sort of the vertices in this scenario, and the connections or the bonds between those atoms as the edges between the two vertices, you notice that there might be an illusion between straight edge embeddings of graphs and molecules. And actually, scientists have been able to physically represent or create a compound in the form of a trephlo, which is the simplest knot. So the hope is that with a little more investigation into linear embeddings of graphs, scientists might be able to develop some compounds that display some pretty interesting chemical properties. But enough background story, let's get to some amazing results. The first one result I want to talk to you guys about is that linear embeddings of K10 are intrinsically triple linked. Well, that looks a little familiar, right? Flappman was able to prove that in every case of K10, every embedding, that it was a triple linked graph. So why am I standing up here telling you linear embeddings of K10 are intrinsically triple linked? Well, as I mentioned, their argument is pretty lengthy. It's around pages 10. They rely on a pretty exhaustive proof, using a lot of combinatorics to prove that there are consequent linkings between all the loops in K10. We were actually able to simplify this a little bit, get it down to about 2 or 3 pages, but we only use linear embeddings of K10 because we can actually rely on the strict geometry of a linear embedding versus a nonlinear embedding to actually simplify the argument immensely. So that was a nice little result that we were able to prove. We were also able to work on Foy's results a little bit, and remember, they were able to remove 4 edges common to one vertex and produce an intrinsically triple linked graph. We were actually able to prove that if we took 5 or 7 of those edges, removed them away from the graph, we still have what we call an intrinsically triple linked graph. And this is actually a product of the fact that if we took 6 vertices from that K10, connect those up, we get what we call K6. And as it stands, in linear embeddings of K6, there are actually only 2 unique linear embeddings. We've got K61 over here and K62 over here. So if we take a vertex from our K10 and concern it in an embedding of K6, as it stands, if we have K61, we can actually remove 7 edges from that vertex to get a triple linked graph. If we have K62 likewise, we can remove 5. So that's pretty cool. But then again, we're still working with K10 here. I want to know, the big question is, are linear embeddings of K9 intrinsically triple linked? Well, linear embeddings of graphs are pretty restrictive. Who's to say that if we have K9, that we're going to even have a triple link? So the first thing we needed to do was we needed to assess whether or not K9 itself had any triple links in them, in linear embeddings at least. And the first thing that we looked at was this notion of linked tetrahedron. So if you look at a tetrahedron, it's really just a triangular pyramid, or complete graph on 4 vertices. And we notice that if we take a triangle that's disjoint from this tetrahedron, and say, link it with all 4 faces of the tetrahedron, so we've got 1, 2, 3, and 4 faces, we can actually link this triangle and get what we call a 4-linked tetrahedron. Likewise, if we take another triangle and link it just around 2 of the faces, we get what we call a 2-linked tetrahedron. Well, we notice that if we take this tetrahedron, give it a 4-link, give it a 2-link, we get a triple-linked K9 subgraph upon removal of one of the vertices of the tetrahedron and its incident edges. So remove all the edges it's connected to. So that's pretty cool. We're also able to push that a little further and say, you know what, if we just have 2 2-link graphs, as long as they link around edges of the tetrahedron that are adjacent to one another, we also have a triple-linked K9 subgraph upon removal of one of the vertices of the tetrahedron. So that's a little hopeful. We've been able to prove that K9 in and of itself in a linear embedding does have a triple link. But what I want to know is if I'm given just 9 vertices, completed graph, is that triple linked? Well, we were able to actually prove that if we are given a 4-linked tetrahedron, like we presented just a second ago, and we take our 2 other vertices, complete 9 vertices, and we have those vertices connect to all the other vertices externally, which is to say that none of the edges puncture any of the faces of the tetrahedron or the triangle, then we get a triple-linked graph. Likewise, we are able to push that a little bit. If we get only 7 external edges of those 2 vertices, but the one internal edge between the 2 actually punctures the tetrahedron or the triangle, we've been able to prove that that is also a triple-linked K9 graph. So that's pretty cool. We've been able to prove that a few families of K9 into themselves are triple-linked. But this is far from a general proof. Obviously, there are many more embeddings of K9 that we need to consider. And some avenues of investigation have been more fruitful than others, and the most fruitful, in fact, has been presented in Flappin's article, as previously mentioned. And in that article, she actually presents the concept of 6 patterns, which is to say that we only have a loop, a closed loop in space, linked with 6 other loops in space, no more, no less. So they've been actually able to present a relationship between 6 patterns and triple links. We've been able to modify that process a little bit and partition our problem, K9, into about 3 sections. The only last section has been giving us a little bit of trouble, but we're actually very optimistic that by the time the joint meetings roll around in December, we should have some more news to present. So with that, I'll end my talk and open the floor up for some questions. Thank you very much.
We have time for a couple of questions, actually.
You said that a lot of times these questions were looked at in terms of knot theory, but that you're looking at them more in terms of graph theory. So what would the knot theorists be looking at?
Oh, that's actually very interesting. My professor has actually been working in straight edge embeddings of graphs for some time now. In previous years, he's actually been looking at K6 and K7, specifically in relation to Conway and Gordon's result. And what they were actually looking for were not only links into a K6, but intrinsic knots in K7. So in addition to the